They can have their electronics on however loud they want. All right, there's my remote. Great. Tonight, Nestor Espinoza will be here to talk about, eventually, after we get through with all the technical difficulties, Exoplanets, a search for new worlds. And we're going to be hearing a lot about exoplanets over the next bunch of years because JWST is going to really do some great stuff, and we are hiring a bunch of exoplanets experts, and Nestor's a brand new one that we just brought on board. Next month, April 7th, we will be talking about 30 years of the Hubble Space Telescope. Yes, it's been 30 years, yeah! And there are 6 speakers, I believe, that will be talking next month. I just got the list. I didn't want to put it all up there, so I just call it an all-star cast of folks who will tell you about Hubble's 30 years and the projects that we are doing to celebrate it. In May, we have our infamous TBA to be announced. June, oh my gosh, I forgot to fill out June. I have a person for June, and I didn't put it down. I'm sorry, that was my fault this afternoon. I was just going through the slides quickly. I couldn't wait to get to the stuff about Betelgeuse, and so I meant to come back and fill this one in. Yeah, there is a speaker already for June. I already have a speaker for June. I just don't have it in my head. Sorry about that. Even astrophysicists make mistakes sometimes, right? As you all are here know, the building is under reconstruction. The lobby redesign is getting there. However, it's not going to be done for the April public lecture. So just like we had to come in through the alternate entrance tonight, you will have to come through the alternate entrance in April. I confirmed that with the building folks today. Everyone followed the signs very nicely the last 2 months. I'm assuming there was no problem this month. And again, if you need wheelchair access, please contact us and we will make arrangements for that. All right, our website for the public lecture series is nice and simple, stsci.edu/public-lectures. And you can find links to the webcasts. You can find the place to sign up for our public lecture announcements. You can find a list of the upcoming lectures, unfortunately featuring the TBA, speaker to be announced stuff that appears there every now and then. Sorry. As well as information about previous lectures. The previous lectures give you the description when it was done, as well as links to the STSCI webcast up top and the YouTube webcast down bottom. You can go back and watch our webcast going all the way back to 2005, okay? You know what that means? We've been doing webcasts for half of Hubble's lifetime. Okay, Hubble's been up 30 years. For 15 years, we've been doing these webcasts, okay? So we can't cover the early years, but we can certainly cover the latter half of Hubble's life on our webcasts, okay? The email announcements, sign up at the website. If you can't handle that and you just want to write it down on a piece of paper and hand it to me at the end of the lecture, please do so. If you have comments or questions, you can send them to publiclecture@stsci.edu. And I will make sure that gets answered. Social media, if you like Facebook or Twitter or YouTube or Instagram, we have accounts for the Hubble Space Telescope, for the James Webb Space Telescope, and some accounts for the Space Telescope Science Institute as well. Myself, I'm just on Facebook and Twitter every now and then. I'm not continuously on it. All right, the observatory tonight, they did schedule it. They got everything all ready. But when I was out at 7:15, there were clouds and it was raining. So I'm assuming nobody will show up to take you across the street. I will check, remind me to check at the end to see if it's cleared up by some miracle and somebody is ready to take you across the street. If they don't happen, just remember on Friday evenings they have open houses. You go to md.spacegrant.org. Check this webpage, the observatory status in that box there will tell you all about whether they're open on Friday evenings. Great. Okay. Now, our news from the universe for March 2020. Our top story tonight, Betelgeuse dimming. It's not cool, man. All right, you'll understand what that means in just a second. So, Betelgeuse is the shoulder of Orion, the upper left in this picture on the right there. That star with the little 4 arrows around it, that is Betelgeuse. It is a red supergiant star. What does supergiant mean? Well, that's shown in this image on the left here. That is an image from Hubble. Hubble was actually able to resolve the star into a bunch of pixels, maybe like 10 pixels across. And you can see the size of the star. You can see the size of Earth's orbit and the size of Jupiter's orbit. Betelgeuse is 1,000 times bigger than our sun. And if it were where our sun is, Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter would all be orbiting inside of Betelgeuse, okay? So that's a big star. All right, and so it's very famous. It's only 700 light years away, so it's been studied a lot. So, Betelgeuse, as seen in 2018, has an average visible magnitude in V-band of about 0.5. You'll notice that the numbers go backwards on magnitude, okay? They get smaller as they go up. That's one of the crazy things about astronomy. A lower number is a higher magnitude. A star of the first magnitude is brighter than a star of the second magnitude, okay? So, Betelgeuse, from our point of view, is a magnitude of 0.5 generally. But if you watched in 2019, you would see that it dipped and then rose back up. What does that tell you? That tells you that Betelgeuse is a variable star. It varies on a regular time scale, about 452 days, I'm told. Betelgeuse has probably several pulsation modes, and the major one is about a 452-day pulsation mode where it gets fainter and brighter and fainter and brighter. They actually call it a semi-regular variable star, and I'm not exactly sure of it because I'm not a variable star specialist, but it is an SRVC, according to the semi-variable regular star folks, okay? Now, in late 2019, Betelgeuse did something different. It went from the bright one you see on the left to the much fainter one you see on the right. Okay, these two images are scaled. Can we take down the house lights a bit, guys? So they can see the detail here. There we go. So these two images were scaled by this guy, Brian Autumn, to try and get the exact same brightness of the background stars so you could see the difference in Betelgeuse. And you can see that in 2019, it's much dimmer than it is in February 2016. Matter of fact, Betelgeuse was dropping below half its usual brightness in December of 2019. So people were watching it, and they got this plot, right? So on the far right, you can see that in late 2019 and into early 2020, Betelgeuse dropped. It went from, it usually goes between about 0 and 1 magnitude. It went down to 1.5, okay? Each magnitude is about a factor of 2.5 in brightness. So Betelgeuse dropped to 40% of its usual brightness. This is the stories you were hearing, like, is Betelgeuse going to explode? No, it's probably not going to explode, okay? It will explode, I promise you. It'll explode in the next 10 million years, but probably not going to explode during our lifetime. We will not, I guarantee you, we're not going to be that lucky to see Betelgeuse explode. That would be an amazing sight if we could see it, but unfortunately, I can't, we're just not lucky enough to see that. So, what's going on? How are you going to figure out what's really going on? You're not just going to measure the brightness of the star, you're going to measure its spectra. And a paper was just recently published by Emily Levesque and Mr. Massey, I forget his first name, and they got spectra of Betelgeuse, and they compared the spectra of Betelgeuse from 2004, which is shown in red here, to the spectrum in 2020. Now, there's an offset between the two of them, and we'll get to that later. But what they were really interested in is trying to measure the temperature, the surface temperature of Betelgeuse. And to measure the surface temperature, you're looking at those absorption lines, the jags that go down, those are the absorption lines. And in particular, the titanium oxide absorption lines are a strong indicator of temperature. The more titanium oxide that forms in the atmosphere of a red supergiant star, the cooler its temperature is. And they found that, yes, there is a difference in the titanium oxide absorption lines, but it's not a huge one. They estimate the temperature in 2004 was 3,650 degrees Kelvin, and in 2020 was 3,600 degrees Kelvin. So a 50-degree Kelvin difference, and unfortunately the error bar on the method is 25 degrees Kelvin. So really not much temperature difference. So the idea that Betelgeuse was cooler and therefore emitting less light is not the reason for Betelgeuse dimming, okay? This is why Betelgeuse dimming is not cool. It's not that it's cooler that it's dimming, okay? I told you I'd get around to explaining my silly puns. All right, so what else could be going on, all right? Well, if you look at a different look at it, it gives you a clue. So here on the green is the visible light, but up here in the magenta and the gray are two bands of infrared, the J and the H bands in the infrared. And you can see back in 2018 and 2019 and now in 2020, they're all the same. Betelgeuse is not changing in the infrared, which, by the way, is where most of its light actually comes out. It's a red supergiant. It emits huge amounts of light in the infrared. Most of that light is not changing. So what's going on? Something is blocking the visible light. All right, so it's like, yo, no, you're blocking the light. Hey, well, that's an idea. Maybe there's a cloud of something in the way, a cloud of dust. And we compare these images, which are taken by the European Southern Observatory. In January 2019, they happened to have that image hanging around. They took another one in December 2019, and you can see that it does look a bit gray. This is another instrument that is able to resolve Betelgeuse into more than just a point of light. So we can see that it looks sort of like maybe there is a dust cloud there. And if you go back to the spectra, you can see there is that decrement between there. And that decrement exists all the way across the visible light, and it gets a little bit less in the blue region, which is kind of what you would expect for dust. Now, it doesn't work if it's small grain dust, they tell me, but the large grain dust that these supergiant stars can blow off, these supergiant stars blow off some dust every now and then, could be the culprit for this, okay? So, it's not due to cooling. It could be due to large grain dust. Have we proven it? No. We will continue to take more and more observations, but things are actually looking up because Betelgeuse reached a minimum on February 22nd. And this is the plot from the account at Betelbot on Twitter, which publishes light curves of Betelgeuse every single day. Keeps you up to date on all the latest observations on Betelgeuse if you want to follow it. You can see that on February 22nd, about 10, 15 days ago, it reached minimum at around magnitude 1.6, which was just a little bit around 40%, a little less than 40% of its normal brightness, and now it's started to rise. And this is, I'm told, reasonable. This is what they sort of would predict if it's undergoing standard variations and such. All right? However, I went through to the American Association of Variable Star Observers website, and I looked and I said, hey, what have you got? And they had this plot here. This goes all the way back to 1911 and goes through to 2001. This is 90 years of Betelgeuse data. And the three orange boxes I've noted there also have dips that extend down to about 1.5 in magnitude. So while we think this is exceptional, this is definitely exceptional under the era where we really closely monitored and really get great observations of Betelgeuse. It may not be exceptional because it looks like late 1940s and during the 1970s and into the 80s, there were at least a couple other times when Betelgeuse dipped down that low. All right? So just this dip doesn't indicate that it's going to go supernova. It's indicative of interesting trends in it, and we'll have more for you on the story eventually. Okay? All right. Our next story. The Sombrero Galaxy mixes it up. All right, so first we got to start with spiral galaxies, and our favorite spiral galaxy is the Milky Way galaxy. And on the left, we see a face-on view of a spiral galaxy with the beautiful spiral arms and a rough approximation of where our sun would be in that spiral galaxy. But what I want to pay attention to is really on the right. Okay, and you can see on the right that in the center we have this nice flat disk, and in the core of that we have this bulge, and around that we have these globular clusters, and then well outside of that we have this faint stellar halo. Okay, and those are the sort of typical structures we find in spiral galaxies. And because star formation is going on in the disk, the young stars in the disk, and they're creating new elements, what you find is that the most metal-rich, which means just heavy element-rich stars, are in the disk, and the stuff in the stellar halo is relatively metal-poor. Okay, so small amounts of heavy elements in the stars that are out in the halo, large amounts of stuff that's in the disk. And we find that's true in other galaxies. We've looked at the Andromeda galaxy, not at the main disk there, but in that small little orange box up there. Hubble took an amazing image called the stellar deep field. And almost every star you see in this image is a star in Andromeda, 2.5 million light years away. We can study the individual stars in Andromeda. How cool is that? And the stars in the halo fit our predictions that they would be metal poor in the halo. Oh, and by the way, on the right-hand side, you see that globular cluster? That's a globular cluster in Andromeda. Yeah! Hubble can get that cool of an image of a globular cluster 2.5 million light years away. That blew my mind when this came out, what was it, 2004, 2005 timeframe? It's great. So, the story tonight concerns the Sombrero Galaxy. And the Sombrero is a spiral galaxy, but it's also an elliptical galaxy because it's what we call a lenticular galaxy. It's got that disk that is indicative of spiral galaxies, but it's got that huge bulge filling out all of space that's indicative of elliptical galaxies. So they wanted to study the halo, the stellar halo of this lenticular galaxy and see, well, do we have some ideas on how it formed? All right, so they took a region that's well up outside it, this region here, and observed it with Hubble. And then within the Hubble view, we're going to take a look at two close-ups, this yellow one and this blue one, to see the stars in the Sombrero Galaxy. Now, we don't see them as clearly as we do in Andromeda, but Sombrero Galaxy is like 12 million light years away. So we don't have quite the same resolution on them. But still, it's amazing we're able to study stars in the Sombrero Galaxy. But what's even more amazing is that it doesn't play by the rules. There are almost no metal-poor stars in the halo of the Sombrero Galaxy, while there are metal-rich stars in the halo of the Sombrero Galaxy. And that gets astronomers scratching their heads. We thought we understood that halos were supposed to be metal-poor, but here we've got one that has metal-rich stars in it. Now, you can see there is globular clusters out in these patches, right? And those globular clusters fit like globular clusters in our galaxy, in an Andromeda galaxy, and they're metal-poor stars in those globular clusters, but not in the field in the halo of Sombrero. We have a thing at our news meetings, and we often go, oh, the headline will be "Astronomers Baffled." Yeah, this is kind of baffling. But, you know, as an astronomer, I sort of like it because it keeps us employed. There are still puzzles to be solved. So we don't actually know how this formed. One of the ways you can get metal-rich stars out is if you have an interaction, okay? Here are two galaxies that are smashing together, and you can see material gets thrown out to huge distances, right? And you could populate the halo with metal-rich stars that way. Except you would also, as you see, disrupt the regular features of the galaxies. And when you look at the Sombrero Galaxy, it's not disrupted. So there was no major merger that we can tell, certainly not for the last 5 or 6 billion years, that disrupted the Sombrero Galaxy and could have thrown metal-rich stuff out to the outside. So it really is a head-scratcher here. So I guess I'm going to give you 2 stories tonight where I'm not really going to give you a bottom line. I'm going to say, hey, this is interesting. We're going to continue studying it, and more information later. I guess that's my whole career, is like, all right, we'll figure this out eventually, and we'll get some things. But yeah, the Sombrero Galaxy doesn't play by the rules. It has mixed it up in terms of the metal-poor and metal-rich stars in its halo. All right. Now, that is our news from the universe. And I know there's a question, come ask me later, because I got to get to Nestor. We're already late because of the technical difficulties, all right? So now we go to our featured speaker tonight. And our featured speaker is Nestor Espinoza. He is in the INS group here, and he can give you what the acronym means, whatever. He's working on the James Webb Space Telescope. He did his graduate work in Chile, where he tells me he was the host of a radio program talking about astronomy. So he has experience in doing that. Then he spent some time doing postdocs and postgraduate work in Germany at Max Planck Institute in Heidelberg. And fortunately, we're able to snare him from there, bring him here, because there's some amazing exoplanet discoveries to be had with the James Webb Space Telescope, and he'll tell you about them tonight. Ladies and gentlemen, Nestor Espinoza.
All right. And can you hear me? Yeah, all right. It's working. And then let me swap to my computer. Oh yes, I don't want to update right now. All right, I'm extremely excited. Once in a couple of years ago, I was exactly where you are seated right now. I remember coming to Baltimore at some point and coming to the Space Telescope Science Institute, which is, it's a renowned institute for doing astronomy and, exoplanet science with the big telescopes in space. I wouldn't have envisioned that I would be sitting here kind of sharing what we're doing with exoplanets. So it's really a privilege to be here. So I'm going to share with you a bit of the science that we are doing in terms of the exoplanets, and which is really a search for new worlds. So because this is such a touching thing for us Earthlings, I really have to give you a little bit of a context on here. And I think the context touched deeply within our human nature. So if you relax for a moment and start thinking of what have we lived here on Earth. So think about every person that has been born, every species that has been grown, every kind of sunset or sunrise that have happened in this planet. Think of every book, think of every scientific fact, every relationship that you have established and that other people have established. So all that has happened, here. In particular, for some of you folks here in Baltimore, for me, back in Chile at some point. And this little pale blue dot, as Carl Sagan used to call it, is just, one little dot in the solar system. Of the now 8 planets, in my heart, there's still 9. So the Plutonians will be happy with me. So this little pale blue dot is just, one in this big, big solar system. And this solar system, of its one star, of the hundreds of thousands of millions of stars in the galaxy. So if this galaxy were to scale here, the sun would be an atom. So it's extremely small. And this is, at the same time, one of hundreds of thousands of millions of galaxies in the universe. So I want you to picture where you're standing right now. So envision the numbers, and I'm going to repeat them. 100,000 millions, billions, as you call them sometimes, of galaxies, and the same amount of order of magnitude of stars per galaxy. So we're just one dot, a small one. So think of the possibilities now. Think of the possibilities around all the stars that you look up when you look up in the sky. So what we know today, for example, is that on average, every star has at least one planet. So if you pick a star when you go out, if it clears out, when you go out and see a star, there's an average one planet orbiting each of the stars that you see in the sky. So imagine the possibilities. So are all these planetary systems like ours? Are all like the solar system? So for example, we were thought that in the solar system, the giant planets are in the outskirts of the solar system, right? These gaseous planets out here. And then in the inside, you have these rocky planets where that's us here. So is this, common? Are we weird or not? So this is one of the questions that you can start answering today. So we live in an amazing era in which we can now start answering these questions. Like, are we weird? How common are planets like Earth, for example? So before we turn into those questions, how weird are we? I want to tell you a little bit about how. How do we go in answering these questions from the exoplanet world? When I went to schools giving public talks, I usually will play this game in which I will ask, kids, what would you do if I gave you, $1 billion and you can build whatever you want? Of course, the last of the priorities were telescopes, right? But if I envisioned them to think about telescopes and I told them like, okay, let's play that you want to find planets. How would you do it? So the typical answer is, well, we'll build a huge telescope and look at it and then try to look for planets around the stars. Extremely simple. Turns out that we can actually do that. So today, for example, this is one of the systems in which you can actually see, so here's it's like a movie, basically, several images stacked in time. And you can actually see planets moving around. So in this case, you can actually see 4 planets by eye here in this picture. And this method of detecting exoplanets, it's what we call direct imaging. It makes sense because you're actually directly imaging the planets. As you can see here, however, the star is being blocked. So the technique that people use to detect planets through direct imaging, what they actually do is what we do when we see the sun is too bright on our eyes. So we just block it with our hands. So we do the same thing, but we put like a small needle in front of the telescope and we block the star, and that's how we get the planets around it. Extremely simple. It's actually extremely complicated, but don't tell my colleagues. So this kind of technique can only be applied, however, for a very, very special types of systems. So very close by stars, for example, very bright planets, usually very young. So this is not really done right now for looking like planets like Earth, for example. So the method with which most of the planets today are discovered, it's actually not with this method. It's with another method that I want to introduce to you using the most famous creatures on Earth, which are cats. I'm not particularly fond of cats, so I'm going to put them in space, but don't do this at home. So here's a star, right, like our sun. Here's a little kitten. So no kittens were harmed in this experiment, by the way. So what you're going to see is that I'm going to put the cat in orbit around the star, right? So at some point, you're going to see the cat happening. Did you see it? Went in front of it, right? So we say, as astronomers, we say, the cat was transiting in front of the star, right? So for those folks that you didn't saw it, here's again. So what we do to search and what we have been using, the technique that we have been using to detect most of the exoplanets to date, is the same thing with the cat, but with planets. So what we do is that we stare at stars and we wait until planets pass in front of the star. So when they do, what happens is that if you look at the light, the star from our point of view at Earth, when the planet goes in front of the star, then there's some light that is blocked by the planet. And then the bigger the planet, the bigger the dimming. And if you observe this periodically, then you have discovered a planet. So the idea with this technique is that you can get first information about the size, right? So the larger the dimming, like in this case, the larger is the planet. So you can get information about the planet, about the star as well, and you can get orbital information about this system. So with this technique, we have discovered most of the exoplanets that we know of as of today. We have found a lot of weird planets out there. For example, as I told you at the beginning, in the solar system, the giant planets are in the outskirts, And then the rocky planets are in the interior part of the solar system. But we have discovered planets that are the other way around. There are gaseous planets going around the stars that are very, very close distances, even closer than the distance that Mercury has to the sun. So these planets, actually, we have seen the atmospheres just blowing out of their planets, which is kind of amazing. We have seen also planets that are large, like almost the size of Neptune, but that they may appear to have rocky, maybe rocky surfaces. So these kind of weird planetary systems make us wonder if we're special or not. So from all this diversity, the largest number of exoplanets discovered to date have been discovered by this mission here. Have you heard of it? The Kepler mission. So the Kepler mission was a mission that basically stared at a region in the sky for like 4 years, just looking for these small dimmings of light, trying to search for transiting planets, we call them, because they transit their stars from our point of view here on Earth. So to date, both adding up the Kepler planets and all the planets from all their surveys that we have been doing from the ground as well, we have discovered so far in the order of 4,000 confirmed exoplanets as of yesterday. So I made my homework, and this is like the latest number. Now, these 4,000 exoplanets have been teaching us a lot about these other distant worlds. One of the things that we have learned, for example, mainly based on Kepler, is what is the fraction of planets based on their sizes. So what you're seeing here is what the Kepler, some folks in the Kepler team call the Skittles diagram, because of the color here. I also love Skittles, by the way, just in case at the end someone has some Skittles to share. So what they have been discovering is that basically the most abundant planets in our galaxy, at least, are these planets that are kind of between the Earth and Neptune, basically this Neptune-sized from super-Earths, more or less. Which also means that living in our solar system kind of sucks, because we don't have this kind of planets. So the most abundant planets in the galaxy are not present in our solar system. That actually hints that we're actually a bit weird. The other important thing that we have discovering, and this is like a huge, huge recent discovery from like the last couple of years, is that if you look up at the occurrence rate of the smaller planets, actually you see that small planets come in 2 sizes. Just as when you buy some clothing, it comes in different sizes. The small planets actually come in at least 2 sizes. So here you have the number of planets per stars based as the function of the relative size of the planets. And you can see that there's one peak here at about 1.2 Earth radii, and another one here about 2 Earth radii. Again, by the way, we don't have any of these kind of planets in our solar system, but they exist out there. Now, the big question is why these 2 kind of planets appear there. Someone just put them there. It has to do with their formation, perhaps. Maybe these ones are gaseous. Maybe these ones are rocky. But the thing is that I have just been telling you right now about the sizes of the planets. So if you pay attention to my words, I was extremely careful to always talk about sizes. And sizes aren't anything or isn't everything, as the Bee Gees said in one of their famous CDs. So I see some Bee Gees fans. That's cool. So sizes, this does not tell us the whole story. There's something more that actually can complement sizes. The reason why we're so focused on sizes, by the way, is because of the transiting method. So if this planet discovery technique that I just told you about, the transit method, we actually measure the light dimming when the planet passes in front of it. And as I told you before, that tells us about the sizes of the planet. But it doesn't tell you anything about, say, the mass or the atmosphere, if it has aliens or whatever. So we really want to know that information, right? Especially the aliens part. So how do we move from there? How do we know, say, that if we see this transiting planet, for example, how do we know that it's a big piece of rock or a big piece of gas? The way in which I'm going to pitch you how we do it is with one of my worst talents that I told my wife that sometime it will be beneficial for me, and this is the time it will. So my wife, you're looking at this. This is my time to shine, which is choosing between fake plants and real plants. I'm absolutely the worst at this, and you can buy a plant for me, and I won't see the difference. Just super bad at this. So I'm going to test it with you. So one of these set of plants is fake. We have the right and the left one. Who votes that the right ones are the real ones? Okay, we have 2, 3, 4. Okay, all right, around, I'm going to say 10% or 20% of us. Who says these ones are the real ones? Oh, God. Okay. I have no idea. You are obviously the experts because these ones are the real ones. And these ones are the fake. You're really good at this. And this proves that my wife is right and I'm really bad at this. However, the way in which I know which ones are real or fake is by a very simple thing. I just go to the plants, lift them up. They're usually the fake plants. They're just full of gas or air, right? Because they don't have dirt. They don't have soil. So they're usually, these ones weigh much more than the weightless ones over there. So this is the way in which I do it. And this is exactly what we do for planets. So what we go, if we want to know if this is a big piece of soil or some gas, then we just go and measure it. Just weigh it. Of course, that's extremely tough to do. So how do you weigh an exoplanet? Well, there's actually a way. We figured this out. So the way in which we do it is basically using or taking advantage of a lie that we were taught in school. In school, the teacher taught you that the Earth orbits the sun. That's not absolutely correct, as Frank pointed out earlier, actually. So what actually happens is that both orbit the center of mass. So whenever a planet orbits a star, the star also orbits around that point. So they orbit around a common point, which is like the average between their masses, basically. It's a weighted average between their masses and their distances. So then the star dances a little bit with the planet. And this dance depends on the mass. So this is actually how we go and measure masses of exoplanets. We just try to watch these dancing stars out there. Now, doing this is extremely tough, though, because you need extremely bright stars from our point of view. So you cannot do it for every star, but we're actually working our way towards that. So what we can do at the end, when you have the radius and the mass of an exoplanet, you can put it in a plot like this one. This is a beautiful plot recently shown by Frugstagli et al., really recent paper, in which here I have the mass of all the known exoplanets versus radius. I have just cut the radius here like from 3 smaller than, they have cut the plot from smaller like 3 Earth radii. So imagine like the size of Neptune more or less down. So what you're seeing here, for example, is where the Earth is positioned, Venus, and all the exoplanets here that we know that are smaller than around 3 Earth radii. So why is this interesting, you might be asking? So look at these curves that you're seeing here. So you're seeing here, for example, what happens if I put a 100% iron ball, and then, for example, for a 2 Earth mass iron ball, it should have this radius, just slightly smaller than the Earth. So we know this, we know the physics of these materials. So we know what they should look like if we created balls of, say, pure iron or half water, half rock, etc. So actually, this tells us a lot of information about the bulk composition of the exoplanets. So this is how we are now trying to figure out what these planets are made of. And we can actually put these exoplanets in context, say, with the Earth and Venus. So for example, this line here, it goes through all what we believe are the rocky planets like our own Earth. So we know that all the planets that more or less cross this line, they're more or less composed similarly, perhaps, like the Earth, at least based on their radius and masses. So the very interesting thing is that, as you see, we don't have a huge sample, especially for the small planets, but we are building this huge sample. And we're doing it thanks to a very, very nice mission that it's right now taking data as we speak, which is the Transiting Exoplanet Survey Satellite. So I've been working a lot with this mission lately. And what this mission is doing is actually looking for planets that are bright enough for which we can measure their masses. So this mission is looking for transiting exoplanets, just like Kepler did. And what it's doing, however, is that it's looking at the whole sky for planets. So what it does is that basically it stares with 4 cameras at a portion of the sky. Each of these sectors goes for about 1 month. So you go 1 month, and then it already did the southern hemisphere, the whole southern hemisphere. It targeted the whole. Then now switched to the northern hemisphere. And then it is surveying the whole sky, basically. So here you see the original Kepler mission. Then Kepler failed a little bit, so it had to change its orbit, its orientation. So these are the Kepler fields. So you can see that TESS, it's actually serving a larger portion of the sky than Kepler ever could. So this is giving us actually a huge sample of exoplanets for which they're bright enough from our point of view on Earth that we can actually measure their masses and put them here. And see, for example, how common rocky planets like Earth actually are. So we can actually start doing that. For the ones that we have masses and radius, it's actually around 400 right now in total. So we're trying to build this sample up. Now, if you want to look for aliens, though, mass and radius does not tell you the whole story. You actually also want to know where they are located in their orbits around the stars. So there's a very important thing for us here at Earth, that we're a very particular distance from the star, right? So if some magic happened and we were put closer to the star, the heat on the atmosphere will just be too much for us to live here. Also, if we were put by some magic in the outskirts from what we are here right now, from the sun, farther away, we will be too cold for life to happen. So there's like a Goldilocks zone in which we can actually be here and perform like a habitable exoplanet as we have been doing for years. So actually this happens for other stars as well. But the distance to which the planets have to be with respect to stars changes because different stars have different temperatures. So there's some stars that are cooler than the sun, for example, and then you can be closer to them to feel the same heat. So it's basically like different temperatures on your heaters, as you might imagine in your house. So here we have, this is one of the most updated plots in which here you're seeing the set of planets in this habitable zone that we call it, which is this zone in which we believe that life could happen if these planets had atmospheres like the Earth. This is a really big if because we have no idea about the atmospheres. So I just told you, for most of the planets, we usually know the masses and the radii, but nothing about the atmospheres. I'm not going to touch on that in a little bit. But I want to highlight one system that is very dear to my heart in terms of a system that has habitable zone planets in it, which is the TRAPPIST-1 system. Have you ever heard of this? No? TRAPPIST, by the way, it's a very good Belgian beer, if I recall correctly. So if you ever go to Belgium, try to get a sip. But this system was, it's perhaps one of the most important to date in the history of humankind. I'm going to tell you a little bit why. First, this was the cover of the scientific magazine Nature that appeared when this system was reported. So it made the cover of the magazine, which makes it really important. But I think this is one of the most amazing scientific covers I have ever seen. I'm going to explain you why. So this TRAPPIST-1 system has 7 planets, transiting planets, by the way. So you can see the dimming going around. And these planets are, in this artistic view of the system, you can see that the innermost planets, they have steam going around, right? That means that basically the planets are so close to the star that it's too hot, and if they had water, it would have evaporated. If you go a little further away, the temperature decreases, right? And then there's no more steaming, and there's actually liquid water. So in fact, there's a set of those planets, these 3 ones here, that could have liquid water in their surfaces because they're at the right distance. However, you keep moving away from the star, like these ones, what do you see here? Ice. So these ones are too far away to have liquid water if they have atmospheres like the Earth. So all of them have more or less the size of the Earth. One's a little bit larger, a little bit smaller, but around average like the Earth. But I still remember the time when I found out about these systems. It was when a colleague that will remain unnamed went to visit in Chile, and we were having some beers. But we astronomers do that a lot, so we socialize a lot. And I remember he told me they were baffled by this system because they couldn't put it together. So the thing with this system is that the planets are so packed that at the time when I was speaking with my colleague, there was no way they could figure out how this system was stable. I want to explain you what that means in a minute. Just so you have an idea, the TRAPPIST-1 system, in terms of distances from each other, so if you compare to the distances here in the solar system, they're extremely packed. So if you could bring them here, the solar system, they will be extremely packed with one another. And the planets will be so close together, he told me, that when they run the simulation, so if you put the planets in a simulation, the simulation just explodes. The planets just float away. So they were like cracking their heads trying to find out what was going on until they heard the music of the planets. And this is what I'm going to show you right now, and I want you to pay attention to what's going to happen. So what's going to happen is that we're going to put the orbits of the planets. They have a period, so that means that they have an associated frequency, sound. So we're going to play the periods as frequency, as sounds. And do let me know when you start to feel the music. So we're going to start with deepest node here. We're going to start adding the planets one by one. So at the beginning, it doesn't sound like much. You'll see how this is going to change as we add the other planets. So they have higher frequencies, right? You start to feel the pattern with a drum. And with the last one, we're going to start hearing a drum every time one planet passes another one. I'm going to cue you this one. A tough one. I'm going to have to concentrate. So look at this planet. Now. This one's going to pass the other one. Now. We're going to do this with all of them. If you want to see more sounds like this, there's a web page called systemsounds.com. It's made by astrophysicists and musicians that got together and tried to make sounds from the planets. So the TRAPPIST-1 system is very special because this sound between the planets means that there's some kind of dance between the planets. So they're not orbiting in random orbits. The orbits are in resonance, we call them, with each other. With this resonance is actually what makes us feel when you hear chords in a guitar or in a piano. These combinations are actually what we think of as music. So that's why you hear music from the orbits of these planets. Turns out that this resonance between the planets was fundamental to understand why they keep their orbits as they do right now, because it's this exact resonance what puts them, what stacks them together. Turns out that resonance, and in general, systems, or there are other systems that have resonances like this between their periods, that are relationships between their periods, they tell you some story about how they formed. So that gives you an amazing data set for you to play with to understand how would you make these systems such as they get to these final resonances that we observe today. So the TRAPPIST-1 system is my favorite system because of many reasons. You know, they have planets in the habitable zone, they're Earth-sized. It turns out that planets like this one, their systems like this ones are really rare. But also, the resonances between their planets makes them, a whole different story. So I have been telling you about distances from planets, masses from planets, radius from planets. But what else do you need to form like an habitable world like ours? You need to have an atmosphere, right? You need to breathe. You need to have a sustainable environment to have life. So this is the next step right now. So this is like the cutting edge science that we're doing with exoplanets, is trying to investigate what they're made of. So what do their atmospheres look like? The technique with which we do it, or the most famous technique right now, and the technique that it's going to be probably the leading technique with which we will discover amazing things in the next decades, It's a method that you can actually see by eye here. So this is an actual picture of a planet going from a solar system planet. If I recall correctly, this is Venus, perhaps. And what you're seeing here is that this aura around the planet, it's actually the atmosphere of the planet, and it's generating some weird effects. One of the effects is that you see this glow from here, and this is actually the atmosphere of the planet. So there's something going on between the light that it's behind, the light from the star, that is going through the atmosphere, and that's imprinting some signatures that you're actually seeing right now. We call this technique transmission spectroscopy for obvious reasons, because basically we're seeing light that is being transmitted through the atmosphere, and we're trying to extract the information from that, from distant exoplanets. So the way we do it is very Pink Floydian. So we basically pass that light through a prism, and then what we do is to look at what light is actually missing from this light that has been dispersed. Because, say, the atmosphere of the planet just absorbed it. So what we do, basically, is to wait until the planet passes in front of the star. Then we wait for light to be transmitted through the atmosphere. We pass that through a prism. We get the information from the atmosphere from there. It's a very tiny signal, by the way. And that's it. You discover an exoplanet atmosphere. What we do in reality, though, is that we measure the size of the planet as a function of the different colors. So the idea behind this is that, for example, water really enjoys, it's the most exquisite thing for water to eat red light. So red light, you put water, you put red light through it, and it will just eat it. So what will happen here, for example, is that you will have, if this planet has water in it, you'll have missing water in the lines here because the light from the red light it's going to be eaten up by the atmosphere. If it is eaten up, that means that the planet will look bigger, because the atmosphere is blocking this light to coming to you. So what we do at the end is to look at the planetary radius, basically, at different wavelengths of light, until we find peaks in which we see that the planet is bigger, and that's it. That's how you discover an atmosphere. We call this a transmission spectrum, for obvious reasons. So I think that one of the most exciting systems for which we have discovered an atmosphere so far, it's a system that it's called, and it's also the most controversial right now in the exoplanet community. It's an exoplanet which is called K2-18b, which is actually a planet in the habitable zone of its star. So, if it has the same radius, the same mass, and the same atmosphere as the Earth, you could expect perhaps habitable conditions there. So for this exoplanet, we actually discovered these two teams here independently, Björn Benekis, who took the observations, Angelo Di Ciara's, which also did a similar analysis to Björn's paper. You can actually see here some signatures in this data that you're seeing here. So this signature that you're seeing here, this up and down, that's actually the signature of water. So this exoplanet in this habitable zone has water vapor, by the way, in its atmosphere. So this was actually observed by the Hubble Space Telescope a couple years ago, but it was just analyzed last year, very recently. And this has hit the news tremendously because, it's an habitable planet. It's a planet in the habitable zones, sorry. But actually, there's one thing that you have to have in mind if you're actually buying your tickets right now to go to this planet. I will warn you that it's not your classical destination to go. Most likely, this planet has a huge hydrogen and helium envelope, like Neptune, for example, in that sense. So I would really not buy tickets to go here, just giving you a heads up. So Hubble has actually gave us a tremendous advantage in terms of exploring the atmospheres of distant planets. But before Frank was mentioning the work that we're doing at the James Webb Space Telescope, that it's set to launch next year, and I wanted to give you a brief heads up on what the James Webb is going to do. So right now, in terms of infrared light, so all the peaks that you see here, all these are different elements that you're seeing here. So right now, Hubble only has eyes for this wavelength range and portions of this wavelength range here. But to gather these ones, which has also other signatures of water, CO2, and these important signatures that we observe in our own atmospheres, you really need eyes that can go beyond what Hubble has done to date. So it turns out that the James Webb, so if you could put the eyes of Webb in terms of the wavelength range that it's going to target, so the James Webb is going to observe this whole wavelength range. So it's going to give us, an exquisite view at these transiting exoplanet atmospheres that we have not yet explored. So I can bet you right now here that we're going to discover stuff that we were not expecting. So imagine the possibilities. So right now we are doing water. What if we discover new things, new combination of elements in these kind of planets, including this K218 that it's for sure going to be targeted by observers with the James Webb. So we're really, really excited about working with Webb, especially in my case, for transiting exoplanet atmospheres. So keep your eyes open for this. I think it's going to be extremely exciting. It's going to be exciting not only because of these habitable zone planets, but also the composition of these atmospheres can tell you a lot about how they formed. Depending where they form, we predict, they must have different compositions in their atmospheres. So with Webb, we're going to start doing this for the first time ever in humanity. And this is really an unthinkable thing for previous astronomers that we're going to be able to do this with Webb. Compositions, formation signatures, it will be basically like standing on these exoplanets yourself. So keep your eye open and keep looking at the sky. Thank you very much.
Okay, I'm here just to help with questions.
Yeah, sure.
And ask one.
Questions? Something about aliens? No. Here and here later.
Crazy question. You talked about resonance.
Hold up.
Hold on one second.
Yeah.
Online audience.
Yeah, just so the folks online can hear you as well.
When you talked about resonance, are you implying harmonics? And if you're implying harmonics, you've got to have boundary conditions and constraints.
Yeah.
And what are they?
Yeah, well, for the TRAPPIST-1 system, right now, so every single word you said actually makes total sense with the TRAPPIST-1 system. And these are actually, so first of all, these resonances put themselves on boundary conditions to the simulations so they don't break. And from there, the current boundary condition that we impose is basically the observed system now. So what people have been doing is that they put them in the resonances as we observe them right now, and then they track into time. So they put like play in the simulations, and they see how it evolves. So the beautiful thing about the resonances is that if you don't put them physically, like these ratios between the periods, this music, the system just blows out in a very short amount of time. But if you put them, this actually maintains the coherence of the system for years and years and years and years. And people, what they're trying to do now is to track them from all the simulation models right now. They're trying to see the fraction of systems that actually generates these resonances without much boundary conditions on these ones. And this is the tough part, because you need to build like a lot of simulations to actually get to the ones that generate the resonances that we observe today. So I've spoken with some of these folks, and some of them are still trying to get this to perfection. But you're absolutely right that there can be some harmonics in some of these resonance systems for sure. Yeah.
Yeah, like a piano string, the two edges are boundary conditions.
Yeah.
And so therefore it's got the harmonics.
Yes. There's so the boundary conditions here are actually the laws of physics, right? Like gravity in this case. So that's what put them together. Yeah. So in the case of the string, it's actually, the gravitation versus the tension, right? So that's what how you build up these boundary conditions. So it's very similar in this case, for sure. Yeah.
So I've read that rather more stars than we can see with the naked eye are actually double star systems. What does that do for planets? Is there many in orbit around such systems?
Yeah, this is a really cool question because there's tons of people trying to figure this out. So we have discovered planets around these binaries, even binary stars that are very far away from each other. But as soon as you start putting them really close, basically it's like tough first, well, there's like a discussion in the literature is how tough it is to form the planets there. So to be completely honest right now, I think we don't have the number of planets discovered right now to give you like a complete answer of, yes, it's easier to form planets around binary stars, for example. But there's definitely people working on exactly that topic as we speak. The entire career is built on that. Yeah.
Ready?
That's fun.
Good catch.
Hi. I'm thinking of maybe pursuing a career in like all of this. So could you possibly just like tell me like what is like your daily life like? Like when you go and
That's a really good question. Yeah.
get
And
work,
keep it
like,
short, we
what do
only
you do?
have so much time.
Okay. Sure. So the daily life is really fun in general. So right now my time is split between working on web and my own science. But I would tell you that most of my life daily has to do with computer programming. That's like the basic thing for astronomers today. Because you have to analyze a lot of data, and then you let the computer do it. But in Space Telescope, by the way, the daily life is completely different to what I have experienced in other places, because it's very dynamic. So there's lots of instrument meetings, there's lots of stuff to do, there's always things to do with the instruments, calibration, commissioning, happening. So it's very dynamic in that sense. But if you want to take, say, the classical career in terms of academia, like full-time research, it's as dynamic as you want it, basically. So you sit down, you think about your ideas, you develop your ideas. If you are a theorist, for example, you develop your models. If you're an observer, then you analyze a lot of data. But in that sense, life can be as dynamic as you want it in terms of a researcher. What I would suggest, though, is that the career path as astronomers, it varies a little bit between person to person. So you first do your PhD, then you do typically a postdoc. So that means that you do 100% research. And then you get to these staff positions in which you divide your work into half, in my case, technical work for the instruments, and half my own research at the end stage, let's say, like that. But if I can give one advice, programming is like the main thing right now. And it will simplify your life even if you don't become the same path of astronomer that you're thinking right now.
And I would add to programming collaboration, okay? You're going to work if you're in astronomy, you're going to work in big groups, and you're going to collaborate with people across the country and around the world.
Yeah.
So learn collaboration and programming,
Yes.
and I think that'll help you.
Yeah.
All right, next question. Good throw. Over here.
Have you got any insights from studying exoplanets that help us understand the formation of our solar system?
Right. When I said that the solar system was weird, I really meant it. There's an actual couple of papers. One of them, a series of them, led by Geek Smulders from Arizona. Right now he's in Chicago, though. That have been studying the population of known exoplanets. We can actually now say, hey, the solar system is actually pretty weird with respect to what we see around in other stellar systems. So yes, we can learn a lot right now, just now, about how weird our system is. What I'm really excited, it's the next step right now. How weird are atmospheres like the Earth? That's really the next path, I would say. And right now we have no idea of this. So say, for example, people always think that when we discovered a planet with the radius and mass of the Earth, at the orbit that we see the Earth around other stars, oh, that's Earth 2.0. But think about that for a minute. Could it be that maybe Venuses around there are actually the most common in the galaxy? Could it be that planets like Mars, perhaps, are the most common? We have absolutely no idea in terms of the atmospheres right now. And that's where we're heading.
So no planet number 9 or 10 for our solar system yet.
No what?
You're not going to find planet number 9 or planet number 10 for our solar
Oh,
system.
in the solar system. Yeah, there's divided opinions in the literature.
All right, so we have a question from online. We had a discussion online about statistics, okay? In that transiting exoplanets are going to be rare. So we're only discovering maybe 10% of the planets via transit, simply because the geometric proportion of that. Then somebody said, what about period? I mean, if Earth's period is a year and you've got to observe for many years, how are we limited in our statistics by the length of our observations, not being able to see the very long period planets?
Yeah, this is a really tough problem right now. So I think this person know about what we're doing in the sense that right now, the mission that has observed the longest period so far is Kepler. So Kepler spent like 4 entire years, targeted at the same region. So we do have statistics on long periods, but so far, we have not detected one planet in the same mass, radius, and period range as Earth. However, we do extrapolations to learn about the occurrence rates of those periods. But to be completely honest, those extrapolations might be a bit dangerous. There's some statistics that you have to pull out here. Right now, this is an issue for sure. This is an issue that has to be addressed by future missions, like the Plateau mission from ESA. That's going to be pretty good in joining these 2 data sets and seeing what you can say in terms of the occurrence rates of planets like Earth, for sure. But this is an issue that we account in the most, for sure. So this transit geometry, people, when they do occurrence rates estimates, so how common are planets around, solar-like stars at this distance from the Earth, this is being accounted for whenever you read how common those kind of planets are. There's an error bar associated with that, and we think we understand that error bar pretty well.
I mean, because like our first planets were discovered in the 90s, less than 30 years ago, and Saturn takes 30 years to orbit the sun.
Exactly,
So
yeah.
discovering a Saturn-sized planet in a Saturn-sized orbit would only just become possible to see one full period right now.
Exactly.
Yeah, that's so got a lot
We
of
are,
limitations.
though, working a lot, and this is a work that I am personally doing, on what we call single transitors. So I told you that, yes, you have to observe several transits to get the period, but that's not entirely true. The shape of the transit light curve actually gives you some information about the period that you can extract, even if you observe only one transit. And we're actually doing it, and we have nailed down a couple systems like this, but they're still not published, but they will in the near future.
All right. Okay, other questions here?
Yes, following up on the young man's question to you earlier about career in astrophysics, and also I'm thinking of a career change as well. Does it pay well?
I think so, in the sense that I now can live very comfortably. You won't be a super millionaire for sure, but you can live comfortably. I think the most complicated thing about a career in astrophysics has to be the movings. So moving, I have moved 3 countries right now. And I mean, there's people that have moved 10 times or more. Once you finish your PhD, when you move to postdoc positions, in this 100% research sometimes, they're usually short limited, 2, 3 years, 4 years if you're lucky. And then that means moving a lot between continents. And that's the toughest part, really, like family. And but money-wise, the career as an astrophysicist pays well, I think.
You'd have to deduct moving costs from all that, obviously.
Yeah, I mean, if they want you, like here, for example, they pay for your relocation costs. So
Some of them, we're not like real business, okay? All right, come on. My wife works in real business, and
But
real
space-
businesses do a lot more. Academia, they give you a little bit of
Space telescope is really special in that sense.
Yes,
because
Space Telescope is
it's
better
really
than
like a
most.
business.
It's a professional salary, but it's nowhere near top tier type
Yeah.
professional salaries.
For sure, you wouldn't make more in industry. Yeah.
Oh, really?
Yeah.
Well, actually, the guy who was second in line for my postdoc at Princeton, he went to Wall Street and earned many, many times what I did at Princeton, okay? So,
That's true. Yeah.
Have you discovered any moons, exomoons?
Oh, not me, but there's a couple colleagues working on this, David Keeping and Alex Tichy. So Alex Tichy led a candidate exomoon a couple years ago that, to be completely honest, is still debated in the literature, but they're trying to follow it up very heavily with space telescopes like the Hubble. There's one signature in one Hubble data set and in a Kepler data set for this exomoon. The thing is that it's a moon the size of like Neptune orbiting a planet like Jupiter, which is, right? So it's like, that's pretty weird, right? That's not what we think about moons. But to be honest, one has to keep an open mind in this business. Sometimes stuff happens that it's outside the solar system. We have seen it with planets. Why not with moons?
like, look, if we were in another solar system observing our solar system,
yeah.
we wouldn't believe that an Earth could have a moon the size of our moon, right?
Exactly.
It would be like, no, that's crazy,
Exactly.
right? So,
Aliens might be laughing at us right now.
Grant, there's one way in the back.
That's true. There's worse things happening right now.
Okay, while Grant travels to the back of the room, there is one question here online. How stable is TRAPPIST-1? Does it flare, have coronal mass ejections more or less than our sun? If those planets are in so close, solar flares can do some damage.
Yeah. So it turns out that the star is a very small star. It's like the size of Jupiter, more or less. So it's, it's a really weird star in that sense. And it flares a lot. Yes, that's true. So there's huge concern for the aliens living there, that they might be experiencing huge flares. That's something that's definitely happening. So the atmosphere would be bombarded by some radiation there that it's important to take into account. And that's what makes this system so interesting in that sense, because it's something we have not seen so far. What happens, for example, maybe we can learn what happens to atmospheres like ours if we are bombarded by these kind of huge energies. So yes, it's a concern, but it's also a source of study.
So TRAPPIST-1 might have some barbecued planets.
Yep.
Okay.
They might.
All right, last question goes to the back row there.
So when you were talking about the most common planets being 1 to 2 to 1.4 times Earth, so we think that the moon was part of the Earth at one point. Are you including the moon in the mass of the Earth when you say that? Or are you actually, no?
It's only planets so far here, right?
I guess what I'm asking, when you're saying 1.2 times Earth, like when we think that the moon was once part of Earth.
Right, we're not including that size.
Your 1.2 is not including the moon, it's just including the Earth.
Right, but also, right, if we put the Earth in that sample, it's just one among, huge. I mean, I see your point that the Earth might be a little bit larger, perhaps, in the past, but it's just a little bit. I don't think it's extremely for the precision that we have right now, and given that the Earth is one data point in the 4,000 data points here, it might not be that important. But you're right.
Okay,
that
And just for reference, the moon's mass is only 1% the mass of Earth.
1%.
So it's not that much of a difference.
Okay, very good.
Definitely below our error part.
Yeah. So the idea that the moon came from the crust of Earth, it's got a lower density, much lower density than Earth's density. So even though it's kind of big, it's low density all the way through.
Right. Okay.
All right. You're going to give one more question? Did you have somebody? You're headed somewhere? Oh, right, we're done. Okay, great. You had purpose to your walk there, Grant.
We believe you.
No, we're getting late. It's about time to go. I need to ask, is anybody from Hopkins across the street going to do observing? I didn't expect so because it's cloudy. No. Fantastic. All right, next month, April 7th, 30 years of the Hubble Space Telescope. We're going to do it. Let's give Nestor another great big hand.